Okay, do you understand, ladies, you are worse than an elephant in terms of walking on a floor? When you walk in stiletto heels, you put more pressure, you put way more pressure on the floor than an elephant would. A big elephant.
I don't wear stilettos. I don't do that.
Okay? It's one of the reasons why a gym coach, particularly the head basketball coach, goes apoplectic when they see females on the floor. Because if you're walking in high heels, you are damaging the floor. And it's simply because of pressure. All right, so what's pressure? What does it mean? What are the units? What's the concept? Force per area, absolutely. So that when you think of the elephant standing on those huge feet, a lot of weight, but boy, a lot of surface area. When you take one of your little itty bitty stiletto heels, right, you're putting all of your weight, much less than the elephant, but on a unbelievably small fraction of the surface area. Your pressure becomes much higher. All right? Now, if you are getting a shot, do you want a sharp needle or a dull needle? Why? Because it's not the force of the needle that actually hurts. It's the pressure that has to be put on to puncture the skin. If you have a really sharp needle, it goes in, they fill you in with whatever the shot is and pull it out. No, it's over, it's great. Right? When you got to push it through and you bust it through and all, that really hurts. Don't do that. Okay? So those are some of the things that we look at. All right? Any fluid can exert a perpendicular to the surface. And what do we call that perpendicular force to a surface? It is a pressure, but what else, what have we called it? We actually haven't really talked about that. All right, we're going to do something that you're going to get in the next unit. Okay? Surfaces. When we talk about forces, we're going to real quick on this. There are two types of forces, and only two types of forces. There are field forces and contact forces. All right? What would be an example of a field force? Magnetic field. Okay, I can apply a magnetic force on a moving charge. If the charge is not moving, no force. But it's a magnetic force because there's a magnetic field. Right? Y'all know that there's a magnetic field in this room. Yes? What direction is the magnetic field pointing? Average magnetic field pointing in this room? North. That is correct. So it's pointing that way. Right? And it's really small. The Earth's magnetic field is really small. But to birds, it's really important. Why is it really important?
So that they can migrate to the correct location?
Absolutely. They actually have an organ inside their brain, right? And y'all know that you ingest iron. Yes? Mm-hmm. Okay. Well, that organ collects magnetic iron that's been magnetized, and it turns or twists according to where the magnetic field is, and they can read the magnetic field that way. That's pretty cool. Okay, and they know what direction to fly. You do understand that the Earth's magnetic field changes places about every million years? Changes direction? Who's that really bad for then? Birds. Me? I don't care. But if you're a bird who thinks they're flying north, right, for a beautiful summer, and they're going out over, heading south, it's just a bad thing. It's worse for the winter. So anyway, there are things like that. So field forces. I have a magnetic field, therefore I get a magnetic force. I have an electric field, I get an electric force, right? What other force? One other field? One other major field?
Gravitation.
Gravity. Is there not a gravity field in this room? Now, there is a gravity field because of Earth. Actually, every mass, but it doesn't really matter. Earth is the biggest one here. So if I let go of the pen, what happens? It goes down. Why? Because Earth's pulling it down. The direction of the gravity field in this room is down. Right? It's actually pointing to the center of the Earth, but we call it down, and we're in physics land, so that works. All right? Now, there's a gravity field here. If I put a mass in the gravity field, it experiences a force. So there are field forces you don't have to touch, because when I let go, am I still touching it? And when I let go, as it's falling, is the earth touching it? But is the earth still applying a force? Yes, so a field force does not require a touch. Therefore, the other kind of force is a touching force. If you're not touching it, you can't apply the force. All right? And a surface can apply two different forces. Right? One of them is perpendicular to the surface. So if this table was frictionless, could it still hold the bottle? If we assume the table is absolutely level, yes. Right? Because it could still push up on the bottle. And that perpendicular force is called the normal force. In math, normal means it's at right angles to. So the normal force is at right angles. The other force that the table can do is force of friction. That will be parallel to the surface. And then we have tension and all the other things which we're going to get later. But the concept here is normal force. The normal force is perpendicular to the surface. And so fluid gets to exert a normal force to the surface of its container. The ideal fluid, not honey, the ideal fluid cannot provide a frictional force to the surface. Right? But that's a physics land thing. All right? Because how many of you have ever basically used your hose to clean your driveway? Aren't you applying a sidewards force with the water? Right? You hit the top of the leaf, but it still goes. So we're in physics land, we're not dealing with that part. But the normal force is what is providing pressure. Now, normal force is not necessarily up or down. All right? Because if I lean against the wall, what direction is the wall pushing on me? That way. You all realize that if it didn't, I'd fall over. Now I have a question. If the wall's pushing on me that way, how come I'm not moving that way?
Because you're pushing on the equal force.
Okay, if what's Newton's second law?
Every force will make one opposite react.
No, that's third. F equals ma, right? And the total story, and you'll get me again more in class on these things. The force, the net force, equals ma, mass times acceleration. If I am my mass, I am my system, all right? And I agree that I push on the wall pushes on me. That's Newton's third law. But the wall is definitely pushing on me. So I have a force. I have a mass. How come I'm not accelerating? Go ahead.
Because the wall is.
Oh, it has nothing to do with the wall.
Because your acceleration is zero.
I agree my acceleration is zero. But think about this. If the wall is pushing that way, the ground is pushing up, not a problem. Because am I accelerating down through the ground?
No.
No. So the ground is pushing, the earth is pulling me down, the floor is pushing me up, those add to zero. If the wall is pushing that way, and there's nothing pushing that way, I have to accelerate. I can't push me. Have you heard the phrase, pull yourself up with your own bootstraps? It's physically impossible. Seriously, grab the top of your shoes and lift.
Yeah, you can't do it.
Pull as much as you want. You can't go up. Yes?
Isn't that the gravity as an
No,
angle factor?
I'm basically trying not to use friction on the wall up and down. The wall is pushing me horizontally that way. Absolutely.
Because it's giving an equal force as you.
Okay, I want you to do an imagination thing here. I want you to imagine if the floor were frictionless. What would my feet do?
Slide out.
Why are they not?
Because of friction.
Because there's a force of friction going this way equal to the force of the wall going that way. Yes?
Yes.
The fact that I was not accelerating guarantees my net force was zero. Has to be another force. And so sometimes you got to look, well, where is it? Or why is it? Or what's happening? Okay? That's the analytical part of reading them when we go through things here. All right? Pressure, as he said, is force per unit area. But it is a perpendicular or normal force. Has units of newtons per meter squared. think. Pretty sure this is 1 kilogram. Right? So how many newtons is this? Weight is mass times acceleration, mass times gravity. So 1 newton times 9.8, but 9.8 is really close to 10. Right? So this is 10 newtons. Right? So 1/10 of this over an area this big. Can you follow that 1 Pascal is really, really small? All right? But pascals are the SI unit. It's a made-up unit, but it's a nice unit. 1 Pascal is 1 Newton per meter squared. 1 atmosphere. So what is 1 atmosphere of pressure? Because in chemistry, did you use 1 atmosphere?
Yes.
And what was 1 atmosphere equal to?
Standard pressure, but ideal gas.
Okay, standard pressure was 1 atmosphere, so I'll take that. But what else? You had other values you could use. How many torr? 760. And what else? What else went with the 760?
760 millimeters.
Millimeters of mercury. Because 1 torr was equal to 1 millimeter of mercury. Okay?
101.3. And I think there's 4 digits.
Oh, almost. Well, it is 1013, but there's a whole lot more to that. No, she's right. 1 atmosphere is 1.013 times 10 to the 5th pascals. Yeah. There, you need a lot of pascals to get 1 atmosphere of pressure. Okay, well, what does that mean? Let's look at this for a second. All right. If we think of that this table is, right, a little more than a meter and a little less than a meter. So let's say that one of these tables is 1 meter squared just for the heck of it. Right? Why is there an atmospheric pressure pushing down on the top of this table? Where does it come from?
The air molecules running into each other.
But why? Because there's a column of air that goes for miles. If I have a brick on the ground, right, it's a nice brick, and it just sits there. But if I put a brick on top of it, doesn't the brick underneath feel a load on top of it? And if I put another brick on top of that one, doesn't the bottom brick now feel the load of 2 of them? So if I keep piling air molecules on top of each other, what's the bottom molecule feel? The weight of all the ones all the way up to the top. Y'all follow? Now, what does that mean to pressure as you go up? It goes down. Does that not make sense, though? That's a pretty obvious conclusion. All right? So air pressure is going, but let's say how much. If this is 1 meter squared, what is the weight of that column of air? I want to know the force. Force over area is pressure. If I multiply by area, don't I get force? By the way, as I'm looking at this, you want to sign, as you signed up for AP1, the computer homework, you want to sign up for this one. It's 195.02. Same thing, just to request a new course. And there is a fluids homework up to work on. All right? So I take my pressure, right, times 10 to the 5th. Isn't that 100,000? So basically, this is 100,000 newtons. Right? I'm going to try to convert this. So we have 100,000 newtons of weight pressing down on the top of this table. Okay? That's 10,000 kilograms worth. All right? Multiply by 2.2, that's 22,000 pounds. That's like 10 mid-sized cars. I am stacking 10 cars on top of this table. Why the hell doesn't this table break? You think these legs can hold up 10 cars? Not a chance. How come the table doesn't break? More importantly, how come you don't go pfft? Oh, sort of. You're really close.